Okay.
Okay, I think I did that right. Okay, well, I suppose, oh, this is nice. The default setting has it pointed so like you see the back of the projector. Oh, okay. Sorry, you get to see the back of the projector. Okay, so I guess we should get started because it's like 4:03. So welcome everybody to our, this is that I know of, the first time we've ever done a joint PICUP ALPhA webinar. I should thank my co-presenter who you don't see here with me, Eric Ayers, for helping set up the jointness of this thing. So welcome. Just a couple of housekeeping items. One is that this is being recorded and will be posted on the PICUP website for people to view later if they like. So just be aware that you are being recorded. The other thing is that I know it's hard to interact very well via Zoom, but I really would appreciate if you stop me and ask questions whenever you have questions or comments, because it's hard for me to see the chat. Actually, Karen, maybe if you could monitor the chat, and if you wouldn't mind, like, you know, waving your arms frantically or just cutting in and interrupting me if I don't notice.
Sure, I can do that.
Thanks. Okay, so I'm Nicholas Nelson. I'm at CSU Chico, and I'm going to tell you about this project that really it's sort of across our department, but myself and Eric Ayers started in on several years ago, which is really examining the way we teach the various methodologies of physics research in our classes. And then I'll give a specific example of a way that we've combined experiment theory and computation in our upper division mechanics class. So I just wanted to put up data because data is always useful. This is the actual breakdown from the American Institute of Physics of the research method by subfield. And you'll notice that they don't actually break out computation. I assume it actually is lumped in with theoretical, because if you look at the second bar from the top, it's computational physics. And interestingly enough, there is some experimental computational physics, which I would like to meet those people. But basically, the point that I'd like to make here is that we really do define ourselves as physicists based on the way we do research, right? Whether we do theory, whether we do computation, or whether we do experiment, or if you're, you know, in some cases, your observation, which I will sort of lump in with experiment. right? We sort of have these three spheres of ways of doing research. And as you can see, different subfields have more experimentalists or more theoreticians, but everybody has this distinction to some degree or another. And this really has sort of boiled down into the way our students experience their upper division coursework in physics. So this is actually from a paper in the SPS Observer, which if you've ever perused the SPS Observer, it's a great place to go to see how our students are thinking about us. Because it's full of articles written by students to other students. And obviously they know that faculty can see it, so it's not like we're eavesdropping on their conversations, but in some sense we are. And this is from a nice paper that was talking about the ways in which people do physics. And they made this lovely Venn diagram that shows these sort of three modes. You have experiment, theory, computation, and then some of this idea of where things overlap, right? And this diagram was in this article designed to help students understand the various ways we do physics research, right? And even more so, it's come down to the way we teach our classes. So this is the upper division physics curriculum at Chico State. And I've left off our, we have a communicating physics class, which I would argue is if there's a fourth branch, that's the fourth one, but it sort of cuts across all of them. So we'll save that for another day. But you'll notice that we really do have this breakdown into theory, computation, and experiment. And I suspect the same is probably true wherever you are, that you have upper division theory classes like math methods or thermodynamics or quantum mechanics. You have maybe one single computational class. In our case, we have a class called computational physics. And you have your lab classes, your experimental classes, right? In our case, we have electronics and advanced lab, our 2 semester-long lab courses, one sort of a junior level, one's a senior level. And then our optics and lasers courses are very much lab classes as well. The E next to those indicates those are elective classes. So our traditional physics major doesn't require students to take quantum mechanics 2, computational physics, optics, or lasers. They have to take some mix and match of those or possibly other courses that they can argue with the department chair. So I suspect this is fairly common, right? This is most places that I've been or people that I've talked to, they have this same general framework of you have your, the upper division, you have your theory classes, you have maybe a computation class or maybe a couple of them, and then you have your one or few upper division lab courses that sort of crush everything together. And interestingly enough, that's not how we teach lower division physics traditionally. Traditionally, the labs are integrated into lower division physics. And if we do any computation, it's not its own lower division class in most cases. It's usually integrated into a single class that also has the lab and the theory. If we make the Venn diagram of the way our courses look, I would say it looks something like this. And if you talk to somebody else here at Chico State, they might put things in slightly different spots. But I would argue that this is the way our courses are currently structured, or maybe how they were structured a few years ago. The theory classes were really theory classes. And the computational physics class, of course, is very computational. Electronics and advanced lab are very experimental. Lasers and optics are sort of special hybrid classes because there are some very serious theory pieces to those courses, but there's also an awful lot of lab work. And so they're sort of hybrid. A few years ago, Eric Ayers and I got talking over lunch and we got talking about how wouldn't it be nice to actually build some computational pieces into all of our upper division physics classes. And then we got talking a little more and we decided, wouldn't it be nice to build some lab components into all of our upper division physics courses? instead of separating them. And then eventually we got to the point where we decided, let's actually try to do it. Let's actually try to see where we could put computation and experiment and theory together in our courses. So if we rearrange this Venn diagram, this is how we think it could work, right? With one possible exception, most of our quantum is going to stay theory. We do have a double photon something or other experiment entanglement piece that that Eric has been working on. By the way, I should note, I don't know if I ever said this, Eric was supposed to be here today. I scheduled him like 2 months ago, and then I reminded him Monday, and he said, "Oh, I forgot I'm supposed to be teaching this class," because he's covering for another faculty member who was out today. So you may give him grief accordingly. I certainly will. Anyway, so this is sort of the way we drew it up, right? That maybe there are a few classes that should purely be theory or pure computation or pure experiment, but for the most part, most of our classes should live in these intersections between the different breakdowns, right? And specifically, we tagged 3 of them, our mechanics, thermodynamics, and E&M classes, as places where we could actually do all 3 at the same time. We could find ways to have lab experiences, have computational experiences, and do the traditional theory work all at the same time in those classes. Okay, so I want to pause for a second and stop just rattling on and do a little exercise here where we talk about, is this a good idea? So either, I guess you could do it in the chat or just unmute yourself and blurt it out. I want some pros and cons for this idea. This idea of sort of putting these classes into the sort of, the sort of intersectional areas of the Venn diagram versus keeping them in sort of their own areas. So what are your thoughts? Give me some ideas here. Why would we do this or not? Okay, appropriate spaces. Ooh, that's a good point. I'm going to try to keep up with the, oh, nope, that wasn't what I wanted to do. Oh, nope, now I quit out of the thing. Let me get back. Okay. Now I'm flipping back. Let's see if I can type from a distance. Okay, there we go. All right, so sorry, I'm not keeping up with the chat. Appropriate spaces. That's kind of a pro and a con. I'll put it in con because I suspect most of us have space constraints, right? We're in a building that was meant to have like classrooms that people sat at desks. So I'm going to put appropriate spaces. Okay, better reflects what we actually do. How many hours per week? Oh, that's a good question. The ones we're talking about, mechanics, thermo, and E&M, are all they are all currently scheduled as traditional lecture courses. So they meet 3 times a week for 1 hour each. We do have the ability to, without changing the units on the class, move those to what are called discussion classes, where you meet for maybe 4 hours a week. But there's a corresponding expectation that you would reduce the homework, the out of class component, right? So there's some games that can be played there on our end. But basically, these are traditional, you meet for 3 hours a week kind of classes. Let's see what else is in the chat. Okay, programming it. So it's good for computational physics. That's a good pickup answer right there. So programming in multiple ways. Okay. Okay, there's we might not be able to cover as much, right? That's always the issue. Anytime you talk about one of these things, right, is you always have to worry about, are you covering the content, right? And I am not an education researcher. I like some education researchers, but I'm definitely not one. I will agree with the concern completely that on some level, students just need to see some things, right? They just need to see, you know, conservation of angular momentum, or they just like, even if you don't have a week to spend on all its glory, sometimes they just need to see things. So yeah, the content. I'll put content coverage. Okay. Ooh, difficult to evaluate. That, do you want to expand on that? Karen, I don't know if you can unmute and talk, but I'm interested in hearing more about that.
Yeah, well, the thing is that if you're going to evaluate something, you need to prepare some, I don't know if it's going to have some computational part, some experiment and some theory. Should do it all in one big evaluation, should evaluate the different aspects, should evaluate by content or by method.
Yeah, that's a good point. Okay, so there's a lot of complexity there, right? Because if you look at the way, at least in my experience, the way we grade lab courses is very different than the way we grade theory courses. And, you know, as a lot of the PICUP folks will tell you, the way we grade computational courses is often a bit of a mess anyway. Okay, that's a good point. I like that. Okay, I'm just working my way through the chat. The pro allows us to choose methods that match problems. Okay. So we can match methods to problems instead of being sort of dictated what problems we can look at. I think this is an important point. And Edward, thank you for bringing that up, because I think this is key. When you do research, you don't get to pick if it's a linear equation you're dealing with or not, right? You don't get to pick if this thing can be detected by, you know, this CCD or that CCD. Your reality dictates these things. And so you have to match the way you approach the problem based on reality. Whereas oftentimes I feel like a lot of times our problem selection becomes almost comically limited because, you know, it's hard, right? And so we have to do the infinite square well because we can do it analytically, but everything else is hard, so we don't do that. Yeah, I think that's an excellent point. Oh, more staff for a single class or teachers to develop more skills. Okay, so I'm going to put instructor skills, right? This gets to a point that we've actually run into a number of times. No one will confuse me with an experimental physicist. I like to joke, when I was an undergrad, the version of Advanced Lab, we had to buy these little breadboards. I don't know if any of you guys use the little disposable, like $1 breadboards. I think they were like 50 cents back when I was in undergrad. I eventually ordered the bulk container of those because I fried so many of them, so many of them. And that was when I knew that I was not destined for a life of experimental physics. So yes, that will be a challenge, is coming up with lab experiences in theory courses for somebody who's not an experimentalist, who tends to light things on fire more than make them work. So that's a great point. Okay, Ernie said, who decides the content? Ooh, that's kind of a con and a pro, depending on your department, right? If your department is structured like some departments I've seen where you know, like somebody owns quantum mechanics, or somebody owns the electronics lab, or somebody owns, you know, thermodynamics, then yeah, there's going to be some issues. Like nobody likes it when somebody comes in and tells you how you have to teach your class. On the other hand, I do think there's some potential there for this giving you the opportunity to have good discussions about what are we covering and how can we make our coursework integrate better. So it could be I'm going to put it on the con side, but it could be a plus. Okay, so I can spell content decisions. Equipment. That's one actually that we've run into. There's a funny story about that. I have this lovely setup that I'll show you here in a minute for my example, that I actually pirated the equipment from one of our other instructors who needs to use it. We thought needed to use it tomorrow. Turns out he doesn't, because tomorrow is Cesar Chavez Day in California, which is a holiday. But everybody forgot about that. Appropriate culture. Ernie, what do you mean by appropriate culture?
Okay, so physicists, at least, I guess maybe I'll say traditionally, for lack of a better word, tend to be really independent actors. And as you mentioned, own courses is sort of the way it often is, but not always. So what I mean by appropriate culture, I mean, if the department culture was one of nobody owns courses, we all own the course, we all share materials, and whoever's next up, you get to draw upon the combined and aggregated knowledge and methods and content of everything. That would be a place where this hybrid approach could really thrive. So it's a culture thing here too, a little bit. So that's what I mean. Sorry.
Yeah. No, I think that's, no, I thank you. I think you're absolutely right. I think there definitely is a cultural viewpoint that would make it very hard to do something like this. Whereas you, on the other hand, right, if you think this is important, right, if you think your students would be better served by having a more unified view of your, you know, your upper division coursework as a department, then this might be a good tool for actually prodding you to have those discussions. Now, that being said, there may be individuals that just don't want to do this, right? You know, that's the department chair's problem. That's why I'm not the department chair. But yeah, there certainly is an issue there. I'm not gonna put that in, I'll put it in con. I should put department. Cultural issues. Okay. Carl noted, we've taken to repurposing laptops from biology, putting Ubuntu instead of class. Yeah. Okay. So there's an equipment situation, right? You made the note about equipment earlier. That it's a challenge, but I think generally speaking, is possible to overcome. Yeah. Okay, so we've kind of talked around these things a little bit about sort of the big picture, the abstract. I want to drill down to a specific example. And this is one that when Eric and I dreamed this up a few years ago, we decided we better try it on ourselves first. So at the time, I was teaching our upper division classical mechanics course. And one of the topics that we run into in that class is coupled oscillators. You know, the classic, you know, two masses on three springs in a line, right? And we thought about this for a minute and realized that we could easily build that in an experimental form, right? And I was already doing some computational things, and so we could actually come at that particular problem from all three methodologies at the same time in this class. So let me give you the way that this was presented to students. Let me come back over here and see if that works. Resume. Okay, it's going to make me stop and restart the share. Okay. Why'd you do that? Sorry about that. No, we're still going. Okay, now I think it did it. For some reason, it unmutes itself every time I switch the sharing. Okay, so this is the this is what we do in like an entire class period in one slide, right? But let me walk you through it real quick. The idea here, if you're not familiar with this problem or it's been a while since you taught or took classical mechanics, this is the problem. The idea here is that you've got two masses, M1 and M2, and you've got a, let me turn on my little laser pointer thing. There we go. Okay, so you've got your two masses, and I've set this up so they don't have to be equal, but they could be. And then you've got three springs, and I've set it up so that they are equal, but again, they don't have to be. You could have different spring constants. And if you just use Newton's second law, right, you write the sum of the forces equals the mass times the acceleration. For each of these blocks, you set up a coordinate system, right, where x1 is the position of mass 1 and x2 is the position of mass 2. And you set the zeros of those coordinate systems to their equilibrium spots, and you write this thing out. You get these two equations from Newton's second law. And this is just simply Hooke's law for the springs and mass times acceleration. Of course, you realize that the way you do everything in differential equations is you assume some kind of complex exponential. And if you do that and you write this as a matrix equation, you get this equation here on the bottom. You get a matrix that has the masses along the diagonal. You get the frequency squared times the position, right? Because we assumed a sinusoidal solution. You get this matrix, which is often called the K matrix, which has all the spring constants in it. And again, times the position vector. And if you look at this, you realize this is what's called a generalized eigenvalue problem, right? You have a matrix times a vector equals another matrix times a constant times the same vector. And so you teach your students about eigenvalues, or hopefully they've already seen about eigenvalues. You teach them that they actually mean something now. They're not just this fun trick of linear algebra. And what you get out of this is that you get that there are two what are called normal modes of oscillation, right? And if the two masses are equal and all the spring constants are equal, what you get is a asymmetric mode where the two masses move exactly out of sync with each other, right? At a single frequency, but in always opposite directions, with this frequency, right? 1/2 pi times the square root of 3k over m. And there's a symmetric mode where the two masses move synchronously back and forth. So the middle spring never gets stretched or compressed. And that one has a frequency of 1/2 pi times the square root of k over m. And you tell your students that all solutions of this system could be expressed as a linear combination of these two setups, right? These two modes. So that's the theory bit, right? And obviously I've gone through it very, very, very fast, and I apologize because I tell my students when they're doing presentations not to do that, but I just did. So hopefully I didn't confuse everyone. That's the theory. So that's what I was already doing in my class, right? That's what I assume everybody who teaches classical mechanics and covers coupled oscillators does, right? They walk them through the math. Okay, so, so being a computational physicist, I saw a chance to bring in a little bit of programming. So what I did, and I'm gonna have to stop sharing this, which means my audio is gonna go weird again, and start sharing this other thing. Here we go. Okay, so what I did was create a Jupyter notebook. So this is Python. That I would give the students for this exact problem, 2 masses on 3 springs, right? And it would tell them this is if I, you know, if I have masses of 200 grams and springs that all have spring constants of 10 newtons per meter, and I solve the system analytically, I get that I should have 2 normal modes, my 3k over m and my k square root of k over m. And again, these are the angular frequencies, not the actual frequencies. But then you can actually, I give them this and I say, okay, let's play with this a little bit, right? So we can actually run through and execute all the code and get down here, and it will actually print our frequencies, right? And you can see that sure enough, it actually does. If I throw it through a SciPy eigenvalue finder, right, it actually reduces and gives you the eigenvalues. And then I give them this little snippet of code that creates a fun little animation that just shows the normal mode, right, in a very, very simple animation, okay? And I give the students this code. I just say, it's on, you know, our course website. Download it. We have laptops available. If people can either bring their own or they can just run it on one of ours. And you can actually see what the thing's doing, right? And I let them play with it. So they can come in and they can say, okay, what happens if I change the mass? What happens if I change the spring constant? If they get really exploratory, they might say, what happens if I make the masses different? Because that problem is hard to do analytically. But it's almost trivial to do computationally, right? Where you can say, what happens if I make one of the spring constants different, or 2 of the spring constants different, or 7 of the spring constants different, right? Have 7 springs. Okay.
The question in the chat.
Oh yeah, sorry, what was the question?
Have the students had a Python programming class before this? It's from Floyd.
Most of them have not. So to them, this is more or less a black box, right? I don't expect them to be able to recreate it. I just expect them to be able to take it and hit enter. And there's a couple small things. So for example, they can change the actual value of the masses. They can change the value of the spring constants. And then I have a little thing in here where they can change which mode number to see the 2 different normal modes. So I ran it on 0, I'll run it on 1, and you can see that's the asymmetric mode, right? But no, I don't expect them to understand the Python here. Now, some of them have, and some of them have already had my computational physics class prior to this, and some of them have seen Python in bits and pieces coming through our intro sequence. That's a sort of a separate issue that we're working on, trying to integrate more computation into our intro level classes. But no, I don't expect that they will have actually, I don't expect them to be able to read the code. I just expect them to be able to fiddle the knobs. Okay, so that was where things were 2018, maybe 2017. And then we had this idea, well, what if we actually try to expand this a little bit, right? We tried to expand this in a way that integrates in an actual lab experience. So the way I did that was I told the students, okay, let's do the 3 masses on 4 springs. Now, again, that is analytically solvable. It involves solving the cubic equation, which is a nightmare, but not impossible, okay? But I tell them, let's not do that. Let's just adapt this program. And so as a class, I put them in groups and I asked them to figure out how to change this code to have 3 masses on 4 springs. And we talk about what the matrix would look like. And what we end up coming up with is something that looks like this. So this is one that actually students worked on, and I cleaned up a little bit. But what you'll notice here is that all they did was they changed it. They actually made it so you could have 3 different masses, which we'll play with in a minute. They have our spring constant, and they figured out how to put the spring constant into the matrix, right? And again, they're doing that by hand. They're just looking, it's basically pattern recognition, right? They don't understand the programming, but they understand the pattern, and so they can reproduce the pattern. And then this line of code, this code block has not changed at all. This one, I actually help them with because this is the plotting routine and it requires a couple of modifications. But I more or less give them the change to the plotting routine and away it goes. So if they run this thing, we make our K matrix, we solve for our eigenvalues, and we actually plot the thing, and we get, again, our normal modes. So there's one of the normal modes. There's another one where they all move together. And then the last one. Right? And those are just fun to watch. Okay, so we do this as a class. This is not a homework assignment. We in class actually modify these in sort of small groups. And a lot of this ends up being, there's a lot of debugging assistance provided by me as the instructor because, again, like I said, they don't necessarily know Python. So it's very common to miss a parenthesis or miss a comma or mess up the indentation or whatever problem pops up. I'll note that generally speaking, I haven't faced a lot of resistance on this, even though they don't know the programming very well. And I think that's largely because they're physics majors and they want to know the programming. I've run into a lot more resistance at like an intro level class from like engineering majors who are not interested and don't want to and think it's no fun.
So there's a follow-up question from Floyd about if they've not had programming, why do you not just have a simulation that does this?
We could, right? We could build, I could basically put some kind of GUI on top of this that means that they don't see the guts of the code. The reason I would answer that is that I want them to be curious about the programming. I want them to have seen it. I have a pet theory that is completely unsupported by data, that one of the reasons students fear programming is that they haven't seen a lot of it. And it's simply the reaction, it's new, it's scary, it's weird. You have to, live in your mom's basement to do this. And so seeing the code over multiple classes, even if they're not writing it from scratch, I think has some benefit to sort of normalize programming a little bit. But that's a good point. You very well could do this, right? And I would argue you're absolutely still doing computation, right? Some people get the idea in their head that to do computation, you have to like code in Fortran or something. And I would argue that just running a simulation is already computation. Thank you. And again, I'm sorry I'm not seeing the chat very well, but thank you for the questions. Okay, so the last piece of this is then we actually have a day where we bring the apparatus into the room and I tell them, okay, let me move the camera so you can see it. Okay, yeah, there you go. Okay, so this is the actual apparatus we use. So all this is an air track, right? It's got these lovely metal carts on it, and they're just hooked up by 4 identical springs. And I have them hooked up to a mechanical vibrator with a function generator, so I can control the frequency of the driving, right? And this isn't talking about really damped driven coupled oscillators, but we have talked about that in the classical mechanics course prior to this, a damp driven single oscillator. And so they're kind of familiar with the concepts, right? That you should see as you get near the special frequency, right? The resonant frequency, you should see the amplitude get really big. And that, yeah, so they're at least vaguely familiar with that. It's a pretty simple setup, right? We just had this, we have these air tracks kind of laying around. And this piece is actually used extensively by our physics of music class, which is a GE class that we offer. So the equipment was all hanging out already. And so I bring them in and I say, show me the normal modes, right? I want you to actually do it, actually do the experiment and demonstrate all three of these normal modes. So they have to do a few things. They have to figure out the masses, which of course is very easy. They just unhook things and put it on a scale. They have to figure out the spring constants, which actually they should have done many times in their like very first mechanics class when they were freshmen, but a lot of them don't remember it very well. It turns out that literally just taking a known mass and hanging it on a spring and seeing how far it stretches the spring with a meter stick works great. So they get a spring constant, they get the mass, and then they come over to the program that we used. Oh, I should stop sharing my screen so you can see what I'm doing. They come over and they put those into the program, and the program spits out these frequencies. So it says, for example, that I should get a resonance at 1.3 hertz. So let's actually see if it works. So I'm going to fire this thing up, and it's going to be a little loud, but well, I got to plug it in first. Hopefully it's not too bad on the audio. So that's plugged in, that's on. All right, so there's the carts, and you can see that, you know, if you pluck them, you get some kind of fun, weird, you know, motion that is some kind of weird combination of the normal modes. Let me stop these guys here for a minute. Okay, so now I can come in here and I can turn on the mechanical oscillator. And again, I'm controlling the frequency. But the number said I should do about 1 hertz. So I'm going to turn this down to 1 hertz, and I'm going to turn it on and start it going. And I'm not sure how well you can see it, but this is actually driving just a very small oscillation. And you can already start to see the response a little bit. So I think I said it should have done 1.3 hertz. So you can see that if I turn this thing down, so right now it's running at 1.5 hertz. And if I stop these guys for a second to kind of get them to chill out, you can see that I actually don't get much of a response, right? 1.5 hertz, I'm not near the normal mode frequency, so I get very little response. But if I move this thing down to that 1.3, I should get something more dramatic, right? There we go. Now maybe I'm a little. And you have to do a little bit of hunting. Turns out this one's actually doing better. We get a little better here. There we go. Okay, there you go. You can start to see the response picking up, right? And you still have a little bit of this other mode. But you can see there's my normal mode, right? There's one of them. And I did have to actually turn that frequency down a little bit, which probably means that my springs got a little stretched when I left them like this all day. Okay, so that's one normal mode. Now we just go through and we grab a different one. So this one says at a little under 1 hertz, I should get the normal mode where the sensor doesn't move hardly at all. So let's see if I can do that. Well, that's actually really going. It's pretty good. Okay, so let me crank down here and we'll calm this guy down a little bit. And we'll see if I can get.
So there was a question about how many of these setups are you using in class and how many students per setup from Ernie?
I have one of these setups, and my classical mechanics course generally ranges from about 10 to, I think the biggest I've ever had was 18 students. So when you do it with 10 students, you have to sort of enforce some rotation around. When you do it with 18 students, I actually have them in teams and I say, okay, you guys go get normal mode 1, you guys get normal mode 2, you guys get normal mode 3. And we can fiddle here and actually see if I can get that second normal mode. I'm having to move a long ways off of what I calculated, which means my springs stretched. Well, I suppose that's an ad for fresh springs. But let's see if I can get that third one. Okay, it says that one should be at about. Okay. So that's where I calculated it should be. Yeah, it's getting there. You kind of see them all moving together. There we go. It's getting there. All right. That's pretty good. Okay, so that's the idea. Let me turn this off and we'll talk about this just a second, then we'll open it up for questions. I'll just add a couple of things. One, we've done some sort of informal and a little bit of more formal surveying of students on this. The students absolutely love this particular activity. They regularly cite this as the best part of the class. They love this idea that we actually, we did the problem on the board and then we used a computer and then we actually did it in real life. We all, I think as physics instructors, like hate that thought that like, well, this is physics. I want to talk about real life, right? Because of course, physics is about the real world. But this really approaches that or addresses that, right? Because it is literally all the pieces put together. The other thing I'll point out is that basically to fit this in, I had to drop 1 day of talk about normal modes. So we spend a little less time. We do the general case for normal modes in a little bit less detail than we did previously. That probably means that they're a little less prepared for a graduate level mechanics course. But it also means but they actually understand normal modes as opposed to just having seen them. So I think it's a net positive, but there is definitely a trade-off. Okay, it's 10 till, so it's a good time for me to stop yapping and give you guys a chance to ask questions. So if you have any questions, I'd be happy to answer.
I guess one question I have is, what do you do if a student doesn't show up on a particular day?
That gets at the grading issue, right? That we talked about before. That I don't have a really good answer for that question. Generally speaking, I grade this in the same way I grade my class participation. So it is not a huge component of the student's grade, the fact that that they were involved in this, because it's very much a sort of experiential thing. So it roughly has the same value as any other class day. I have thought about how I might make this into more of an assignment, more of a project kind of thing. Haven't really come up with a good way to do that. So yeah, this is really much more of an experiential sort of thing. Oh, okay. So there's a question in the chat about, actually, I guess I should look at the whole chat. How many other activities do we use? I do 2 other activities like this in my mechanics courses. I do one on drag, on projectile motion with drag, and I do one on solid body rotation. So 3-dimensional solid body rotation. I make them work out the moment of inertia tensor for a mallet, and then do the famous, problem where you flip the hammer and it about its intermediate axis and it rotates. And those are similar. They're more experiential, right? And there's a computation piece for all of them, and there's an experiment piece for all of them. On the E&M and thermo, I will say that those are still very much under development. So thermal has a couple of experiments with entropy in using magnetic domains that I have not personally played with, because that's somebody else's. I haven't taught that class in the past few years. But I've helped out with the coding side of that. E&M, the only one that we currently have is we have a LRC circuit setup where, again, they do the theory, they do the actual experiment, and then they do a little bit of computation for that. But again, by far, the reason I'm talking about mechanics is because mechanics is the most developed of the 3. I should look at the chat. Video analysis. Yes, I will say that I have personally played around that. I haven't implemented it in class. But one of the ways that I originally dreamed this up actually was not using the driver, but just setting it up and just having them hit it, and then using some video tracking to measure the motion, and then doing a Fourier transform to show that there were actually only 3 frequencies represented. That is slightly more complicated, but not dramatically so. And actually, one of the side effects of the pandemic is that in dreaming up ways to do labs online, we have moved much more towards using video tracking because it turns out almost all of our students have one of these lovely high resolution, high frame rate cameras in their pockets. And so if they can figure out how to do it, right, taking video, running it through an image tracking program, Vernier has a good one, or if you want to go the free route tracker, the physicist special, it works very nicely for most things. I haven't tried that, but I think that would absolutely be something we could do. Mechanics really lends itself to that, right? Because mechanics is moving things. And so it was sort of a natural first place for us to go. Any other questions? Okay, well, maybe we'll stop there. Thank you all for coming. And yeah, if people have further questions, you know, you can always reach me by email or on the PICUP Slack. Yeah, but thank you very much.
Thank you, Nick.